My computers scare me. The computers scare me. I said, well, why is that? Well, I just don't understand them. I said, well, that's kind of silly. He says, no, no, you really need to be very, very careful of things that you don't understand. Well, I understand that, but there's no need to be scared of it. I said, for example, you will take and leave this meeting and you will take your key out of your purse and stick it in your ignition and you will turn it and your engine will start on your car. But you'll have no idea what you just did. You have no idea what an ignition system does on an automobile. And then you'll proceed to use another thing that you don't know. You'll put it into reverse and you'll have no idea what an automatic transmission does. I mean, just because you don't know doesn't mean you need to be scared of it. That's an intro to my background of the misunderstandings of computing. And that's gone on and on. After computers came out and became more widely distributed on desktops and office spaces, we took and invented the World Wide Web. And people were terrified of that as well. And things go on and on. Now, everybody's got a little gadget like this in their purse or their pocket. And that's got more computing power than went to the moon and back. There's the scare is just the not understanding of what it is that we're doing and what we're talking about. Speaker tonight is Harmon Carr, and she is one of the newest faculty in the Department of Computer Science. She began last September, I believe, fall term, and she has received her bachelor's degree from the University of Minnesota, and she earned her doctorate degree from the University of Michigan, and she has now done a boomerang, and she's returned here to the U of M. What she will be speaking on tonight, or her area of expertise, and what you'll be speaking on tonight is the human AI interaction. AI is the new thing that everybody doesn't understand at all. And many people are scared of it because they don't understand it. And they throw up their hands and they just don't understand it. And Harmon is here to give us an overview of the decision making, how to explain AI, how AI works. And we primarily as members of large legacy systems, will be listening to understand how and why that can help us in embedding those things into existing legacy systems. And with that, I will introduce our speaker tonight, and she may continue to introduce herself and her topic, Harmon Carr.
Thank you so much, Anthony. I'm really excited to speak with you all. Let me try the full technical thing here of trying to share my screen and see how easily that works out first. And let me know if you all can, in a second, see my screen. And hopefully you're seeing the full view and not a presenter view. So
That's good.
All right. You might hear my cats in the background every now and then. I apologize for that, but other than that, I think we should be good. Thank you so much again, Anthony, for that introduction. And I think your anecdote is going to be even more relevant than you maybe you realized this based on what I had sent about my slides, but it is going to be very relevant as we continue to talk about safety and understandability of human AI systems. But first, I want to maybe explain what I mean when I say leveraging social theories to enhance human AI interaction. What I'm going to talk about is how we can leverage an understanding of how people think, communicate, and collaborate to design more effective and safe human AI interaction. And I'll share more about this as I answer 3 questions during this talk. You're welcome to interrupt me anytime, by the way. There are some exercises in there that we'll do together, hopefully. But yeah, please feel free to stop me anytime. So we're going to talk about, let's see, what is an effective human AI partnership? How can we make human AI interaction safe? And then what can we do to enhance human AI interaction going forward? So starting with the first one, what do I mean when I say effective human-AI partnership? I mean something that amplifies the complementarity between people and AI, that combines their expertise in a way that we can take advantage of what they're each good at. So I'm going to do a very brief example of this, not a deep dive by any means, with visual question and answering. So the visual question and answering pipeline starts with, say, a visually impaired user sharing an image along with a search query online, and then getting answers to the search query. So some examples of this are, what color is this? Or what item is this? Could also be, which medication is this? Or what's in this picture? Now, the first two are fairly simple to answer, especially now with advances in computer vision. Where it gets tricky is that since visually impaired users cannot always clearly see their environment, they can share potentially sensitive information online, right? So here you can see in the medication case, they can potentially share their name and their address that could be on the prescription bottle, or a photo of themselves or some important documents. So potential solution to this privacy issue or sensitive information being shared online is to obfuscate any potentially sensitive content in an image before we share it online. So for example, if this was the original image, if you obfuscate it, with just kind of context of what is in there, but without the actual content, you would be saving, the person's privacy. Now, this isn't as easy as it seems because neither AI nor people can solve this problem on their own. So AI doesn't always understand what sensitive means because it can be context dependent. And people aren't always a reliable form of doing this task. And in both cases, whether that's with AI or with people, you would have to share the original unmasked image. So that kind of defeats the purpose of the original privacy concern. So instead, what we did was we divided this image into segments, and then we had crowd workers look at one segment at a time to tell us whether that segment had potentially private information. And then we had them guess whether the surrounding segments to them could have potentially sensitive or private information. Now, the system design uses the knowledge that people understand this kind of context, right? If we see a nose in a picture, we know that it's very likely there's a face surrounding it. This type of context that AI doesn't always understand. But then the benefit of this approach with AI that we utilized was in optimizing for a budget provided by the user and for making real-time decisions of, okay, if we have 90% certainty, everyone agrees that this surrounding segment guessed is sensitive, then we don't need to maybe show that segment as the middle segment to someone else. So kind of optimizing the cost and what's shown to people is where we used AI. So we used this human AI complementarity to start progressively masking an image from smaller segments to larger segments until you received this kind of one final masked image that was sent to a third-party system for this visual Q&A with visually impaired users. So that's what I mean when I say an effective human AI partnership, where you're taking advantage of what each party is good at. Now, we've developed in my lab several systems like this where we're trying to amplify kind of each partner. But now this is something that you all probably think a lot more about than we do. What about real world deployment, right? So any effective systems that we build, if the goal is to ultimately help people and put them in front of people in the wild, as we try to deploy these systems, there are additional considerations that come up that have, that you don't think about in a research capacity often. So for example, with this visual Q&A system, you might think, okay, this seems like this would help people. We could maybe put this out there. But we're assuming that there are no bad actors, right? So you could imagine that crowd workers working together to adversarially attack the system through a forum to try to get the original image back, even though we're only showing a segment at a time. So there are these ways in which these systems could be misused. And this isn't just true for sort of the research systems that we build, but we're seeing examples of this everywhere, right? This is no longer a hypothetical. There are many similar challenges with biases and missed edge cases that have come from large-scale deployments of human AI systems these days. So that's why I would say effectiveness and amplifying complementarity is one part of my research, but the research that I really want to talk about today is how do we make these systems safe for societal use, for real world deployment?
Question.
Yeah, yes, we have a question.
The obfuscation slide that you had, and any of them, I'm just going to talk generally about that. Two questions. One, the quality of results that you're going to get is very heavily dependent on the quality of the question that you ask. If you put up a picture and say, "What is this?"
Right.
What does that even mean without any more context? That's one problem. The other problem is the obfuscation that you go through may make the whole meaning of that picture irrelevant. If the real thing you're getting, what is this? I want to know who that person is. Privacy aside, you've made that an impossibility. You hide the person and say who's behind the curtain.
Yeah,
those two questions I had.
No, absolutely. Those are fantastic questions. So I would say in this case, our context was very much the helping visually impaired users. And so oftentimes, the situations that they're in, they walk into a room and they don't know what's their surrounding like or what's their environment like. So they'll often take a picture and send this out to these visual Q&A websites. So, what you saw, what is in this picture is often the query that they genuinely have just because they don't know what to expect. And if there's a person, that being the concern, that happens often when they've switched their camera around, they've flipped it around, and instead of taking a picture of their room, they've accidentally taken a picture of themselves and shared it online, right? In order to ask the question of what's in this room. So the examples that you saw there are all real queries from visually impaired users and sort of the types of questions that they ask online. Does that make sense? Answer your question?
Yeah, that's a good start at it.
Okay. But yeah, I mean, I think what you pointed out in terms of, the challenges of this approach would be if we deployed it are definitely also equally important challenges on top of this sort of idea of safety in a real world deployment, right? That we sometimes aren't able to or don't test when we're building out these research scale systems. But we did try to, use as much context as possible from the visually impaired users that we were working with. All right, so the second half of my research here that I really want to focus on today is this delta between innovation and its secure deployment in the real world. And this is where we're asking questions like, what are the incompatibilities between people and AI that cause challenges in the real world, and how can we change system design to address them? So I'm going to talk about a couple of projects here in varying levels of detail. Luckily, I'm not the only one working on this problem of, improving safety in AI. So in trying to answer this question of how we can make human-AI interactions safe, let's consider what's being done in the industry these days. So there's a major thrust of research and application on interpretability and explainability, with the idea being to help people understand AI and machine learning outputs, so that if people who build or use these technologies understand why they're making certain decisions or predictions, we can hopefully catch and fix potential issues that might come up. And there are normally two approaches to interpretability or explainability. There are glass box models, which are essentially things like linear models or decision trees or rule-based models, where it's very easy to tell how a set of input features lead to a particular predicted outcome. And then there are black box models, which are far more common, especially with deep learning approaches. Now here, you can't really tell how a black box model is working, but there are post hoc explanation techniques that try to mimic their behavior and approximate how they're working to give you, again, an understanding of how a set of input features might lead to a predicted outcome. So the types of visuals that you can get with these kinds of approaches, there's normally three of them. So say you were predicting income based on demographic features, you could get a local explanation. So this is about how an individual's income prediction was made. So on the y-axis here are data about a single individual. And then, there's a prediction for whether this person made the classes here are 0 or 1, and 0 represents less than 50K income, 1 would have represented greater than 50K income. So you can get that explanation for an individual data point. You can get relationship between features and the predicted variables. So here is the relationship between age and income sort of at a high level across all data points. And then if you summarized these feature relationships, you could get a global explanation, which is sort of a summary of what the model has understood from the data. So which features does it consider important across all data points? So these explanations now, these approaches that have been developed by several people now, they provide insight into AI, ML sort of model behavior that we did not have before. But the big question that remains is, does this actually work with end users in the real world? And that was sort of the motivation for some of the work that I did, where we conducted one of the first human evaluations of these interpretability tools with data scientists. So this is a stakeholder with some machine learning expertise and familiarity with these concepts. And how we went about it was we started with some nuanced qualitative interviews to understand sort of common challenges in the data science pipeline. We then conducted what's called a contextual inquiry, where we had people use an interpretability tool to sort of, against the challenges identified in the pilot interviews, and then found some themes of problems that kept coming up. And then we conducted a large-scale survey to see if the themes of problems that had come up held up at a large scale, so to see if we could make generalizable sort of outcomes based on the things that we found in our first 2 parts of the study. Unfortunately, what we found was that interpretability alone does not work. Instead, there was a lot of misuse and overtrust of interpretability tools. So less than 4% of the 197 data scientists in our study could even accurately describe the details of the visual explanations that we were showing them. And these are, again, state-of-the-art tools that are publicly available. Most of these data scientists severely overestimated the capabilities of these tools. So here's a visual that shows sort of all of the capabilities of these tools. Some of them are actual features. So these bounded boxes represent actual features of these tools. Everything else is just kind of things we came up with about interpretability in general. And as you can see, people assigned far more features to these tools than they were capable of. And some of these are things that aren't really going to be possible for a long time. So things like automated detection of fairness. Fairness is such a slippery slope, right? It's very hard to contextualize and sort of very hard to have as a concrete metric. We don't even know how to define fairness in most contexts. So there's no way we have the capability of automatically detecting sort of fairness issues at the moment. But as you can see, sort of people, assign a lot more value to these tools in general. And then most data scientists we had presented them with sort of erroneous models to see if they could find these errors in those models. And despite these errors, they gave these models very high deployment scores. So as a part of the sort of study setup, we had asked them to explore sort of a data on income, and we had asked them to use interpretability tools to do that. And then at the end of their exploration, we had asked them, do you think this model is ready for deployment in, a loan application tool? And they consistently gave it high deployment scores. Now I'll give you an example of what we showed them. So one of the relationships that they saw, which has an error, right, is this relationship between age and income. So you can ignore the right-hand side axis here for the most part, but on the x-axis, you have age values, and on the y-axis, the SHAP value for age actually represents its relationship with income. So I'm curious if any of you have any thoughts on this relationship between age and income, and whether you think I've already given it away that there's an error here, but I'm curious if you all have any thoughts on if this is a valid relationship between age and income.
You have age on both axes.
No, so the x-axis,
gonna-
sorry, let me clarify again. So x-axis here is what the values of age are, so 20 through 90 on the x-axis. On the y-axis, where it says SHAP value for age, that means its relationship with income. So shaft value just represents the relationship.
Okay. I misread the chart.
So what we'd done here was we had imputed 10% of age values with the mean age. And so as a result of that, this age of around 38, 39 is where you see that huge spike in the visual, right? And so people saw graphs like this and other graphs where we had introduced errors into the data. And after seeing all of these, they still determined, sort of no questions asked, this model is ready for deployment. And we had asked them some qualitative questions around sort of what they saw in these visuals and how they interpreted them. And one thing that came up a lot with this particular visual was, it's not that they did not notice the spike at all and completely ignored it. No, they did notice it. And the issue was that very few people thought that the spike needed to be resolved before deploying the model in the wild. They made this into a feature rather than a bug because they trusted the tool to tell them if this spike was wrong. Instead, they came up with narratives to justify the spike. So one common narrative, I guess I see Anthony, maybe you're about to suggest something or say something.
I was thinking that being a mathematician, if that curve including that goofy spike was a function, you couldn't integrate or differentiate over that function because of that disjointedness or that non-smoothness of the curve. And that problem has been, if we went over to the mathematics department, all the professors will pound that and pound that and pound that. You can't do that. And that's one of the major failings of not being able to advance in mathematics. And you're pointing out that we've still got the same it's different. Yes, we're dealing with AI things, and yes, we're dealing with things that aren't really functions, but not understanding the base data or the underlying model or the functionality of what's going on and basically violating the rules, you're going to have trouble. You're going to have trouble, and you're going to have big trouble with that. And that's something that hasn't gone away. And I mean, that was true when I was an undergraduate, and that was true when my professors were undergraduates.
Yeah, and it's become worse in some sense now because we've sort of had this push towards democratizing ML, making it accessible to anyone and everyone, right? So now we have these tools that show what's sort of going on inside a model, even if you don't understand how the machine learning algorithm works, right? Here's sort of a representation of it visually to help you figure out maybe you need to pay more attention. But even when people see this, they're not looking for, I wonder what's going on here and let me explore further. Instead, the behavior that's happening is, oh, something's going on over here. Let me figure out a way to justify it, right? So here, with this example in particular, how they justified it was, well, 38 to 39 is when you pay off your student loans and things like that. So maybe you're taking home all of the income that you're generating. So of course there's a spike, right? So it's this human process of justification that's happening on top of sort of a lack of understanding of the nuances of the mathematical modeling that's happening in the algorithm. And both of those together were unexpected and are causing sort of even more problems now.
My background in systems, we had a saying for that.
Mm-hmm.
You may get the best tools in the world, but fools with tools are still fools.
Exactly.
They're still fools.
Yeah, and
you have to understand the underlying principle.
And as a researcher in this space, that's what worries me is we've created more and more of these tools and we've assumed we've solved the problem. But this is as much a human problem as it is a technical one. And that's sort of where my research often is trying to make
Exactly. I agree.
Okay, so this study essentially told us that the solution that the sort of community is so happy about, right, that is purported as this savior to make AI more safe is not quite working. So naturally, sort of, we were next thinking about, well, why is it not working? What's the incompatibility at play here? What do we need to know to fix this? And our exploration led us to conduct more of these sort of human-centered experiments, again, in a quantitative setting to speak to that population level, what's going on. And the thing that we really focused on that, you know, Anthony, you also just mentioned is cognition, right? So we hypothesized that the cognitive framework of bounded rationality was at play here. Bounded rationality essentially says that cognition is expensive, so people apply heuristics as shortcuts to avoid thinking deeply about something. Our brain has two systems, system 1 and system 2. System 1 is the more automatic, intuitive, and unconscious thinking mode. It's fast, but it can be error-prone as a result. And then there's system 2, which is a slow, controlled, more analytical and deliberate thinking mode. It's normally more reliable, but it requires more cognitive effort. And over the years, researchers in psychology and cognitive science have shown over and over again that people use system 1 to avoid information overload and decision paralysis, right? So they lean towards that unless something pulls them away from it. To quickly make decisions, people, like I said, rely on heuristics. So an example of this is the availability-based heuristic, where they use immediate examples of what comes to mind when making a decision rather than, you know, looking at the complete picture. And these immediate examples that come to mind are usually based on recency, frequency, vividness, and other factors about the information. Another example of a heuristic is the imitate the majority heuristic, where given a choice, people tend to pick one that is popular in their sort of socially proximal reference group. Now, we were sort of wondering what these heuristics might look like for a machine learning setting, and how do we capture these? So I'm going to use another example here, and you're welcome to actually try this out on your own. So we looked at the Titanic survival dataset, which uses passenger information from the Titanic to predict whether someone survived or not. So here's the Google Colab notebook if you want to run the code and see what the visuals look like. But I'm also going to show you some relevant visuals here. So again, because of these interpretability tools, now I'm able to get visuals like this global explanation about the Titanic data, which shows at a high level which features are most important to a model that has been developed on top of this Titanic data set. So you can see the sex, the passenger class, the age are sort of some of the most important features. You can also get relationships, again, between one single feature in the output. So here is the relationship between sex, which was divided as male and female, and the rate of survival. Here's the relationship between age and, again, survival. And then this is one person's data. So a single person whose values are on the y-axis here. So age 37, male, first class passenger, and sort of how each of those individual factors sort of led to the prediction. So for this individual on the bottom right, the prediction was that they survived. And I'm going to ask you a question that a lot of data scientists often have to think about as they're building these models. What would flip this prediction from survived to did not survive, right? So this sort of a morbid question, I'm sorry, but you know, if this person on the right, if we had to make them not survive, what thing would we flip to make that happen? And I'll even give you some options. We could change the cabin from D35 to E67. We could reduce the fare of their ticket from $52 to $10. We could increase their age from 37 to 70, or change their sex from male to female. So which of these things do you think would flip this person from surviving to not surviving?
My guess would be age, because that's the predominant one on the bottom graph that takes up the whole bandwidth, and everything else is, you know, 10% of the bandwidth. 10% to 1%. So they are everything else other than age is very lightweight. If that
was my
makes
impression
sense.
as well. That was my impression as well.
Yeah, so we've got some votes for age. Any other thoughts? All right, so let me give you some answers here. So in this case, both 1 and 2 are correct. You can change the cabin or the fare. Now, between these two, cabin is sort of an odd one to reason about, right? Unless you're a really big Titanic fan and have gone and looked at all the schematics of Titanic to see where each of those cabins would be, it's hard to quickly think about what that change would do, right? But fare is sort of easy to think about, right? So if you reduce the fare, you're presumably going from a higher class to a lower class, and the lower class is sort of the decks close to the bottom, right? So if you're in the lower class deck, getting to the top, getting away from the ship might be hard. The other one that you all mentioned was age. So if you increase the age, it might become harder for someone to, again, get to the rafts and save themselves. Now, in this case, without having done any data exploration, it was a valid guess, but this is a first class passenger. So that effect mediates this effect of age. So if you're rich traveling in first class, you still would have survived, even if you're older. So both 3 and 4 are actually inaccurate. But this process that we just kind of went through, where, you know, there's accurate choices that are hard to reason about, and then there are plausible choices that you can reason about, but that could be accurate or inaccurate. This is exactly where we're applying our heuristics, right? We're thinking through sort of what these changes might do based on our knowledge of age or fare. And this is what data scientists are doing all the time, even when they're looking at sort of their own data, right? So we wanted to capture this application of heuristics in machine learning and see what interpretability does to them. So we came up with this range of possibilities based on time and cognitive effort. The axes are time and cognitive effort because they really form the basis of cognitive science for decision making. Now, when you apply deliberate reasoning and spend a lot of time and cognitive effort, this is called the maximizing cognitive mode. So for this machine learning setting that we've been talking about, we hypothesized that this is a situation where there's no interpretability, where you really have to write all the code yourself. There's no tool doing the job for you, providing you visuals, nothing. You kind of have to work hard to get to the answer. The opposite of that is when you have to spend very little time or cognitive effort on something, and this is often called satisficing. And we hypothesized that a lot of the interpretability tools fall under this category. So these interpretability tools show the visuals that I've just shown you so far, right? And when you present these static visuals, it's very easy to quickly say, everything looks good, there's nothing wrong here, or come up with justifications for what you're seeing. So we felt that this might fall under the satisficing category. That was our hypothesis. Now, of course, there's also critical situations that require quick, but very highly effortful, thoughtful decision-making. This we called the surviving cognitive mode. Luckily, this would be something like a doctor making a last-minute decision in a trauma situation in a healthcare setting, right? Luckily, most data scientists don't have to operate in this setting, so we kind of stayed away from this for model interpretability and data scientists using things. And then finally, the fourth quadrant there is what I like to call optimizing. So this is an optimally effortful mode where you're engaged with a tool or a system for a long time, but it doesn't feel cognitively demanding. And that's why I like to call it optimizing. Now, in human-computer interaction research, we learn often that interactivity in a system can promote engagement. You know, when you're able to click through things and really engage with the system, it keeps you going with it for a long time. So we wanted to test if interactive interpretability tools could offer that kind of optimally effortful situation that would keep people engaged for a long time without being cognitively effortful, with the hope that if someone's engaged for a long time, their likelihood of discovering their own heuristics and biases might be higher, so that they would, in the end, make better decisions about the data in the model. So these interactive interpretability tools, let me just quickly show you how they might look different from the visuals that you've seen so far. With these, you can sort of bin, color, scatter plots using different cohorts of data. So instead of just seeing one scatter plot, you can kind of explore it a little bit more. You can also generate counterfactuals for a data point. So you can see how one single data point, what would the nearest neighbor, what would the sort of nearest counterfactual look like? You can look at how age is affected in that particular data point. You can change values of that data point in real time and see sort of real-time prediction of what if I changed age from 37 to 70, how would that change the prediction? So again, it gives you the same information that you might get from a static visual, but does it in a more sort of feature-friendly, interactive way. And all of this is under the data point editor for this, right? There's other charts around fairness metrics, around data distributions that you can access in these interactive tools that are also available. So the tool that you're seeing here is Google's What If tool, if you ever want to try that out. So we conducted a study.
Perhaps this isn't pertinent, but we're talking about identifying and capturing the heuristics that are going on when people are using that.
Yep.
And I have a sense that we want to capture that to kind of get rid of that, or to kind of put a bound or constraint on that, as opposed to letting it run wild. You've shown tools, and I intuitively see how paging through stuff and fiddling around with stuff helps come to the realization of the heuristics. But does it really get rid of that? Or does somebody say, well, yeah, I'm using this heuristically, and this is fast, and this is great, and this just reinforces it. Come up with a self-fulfilling prophecy, or create a model that proves what you want to prove, which really proves nothing.
That is a great question. And we sort of have to take it one step at a time, right? So the first study that we conducted that I'm going to show you some results about is about whether these heuristics even happen, right? So we're assuming that this bounded rationality is happening. That's an assumption we're making, but there was no proof of it in this machine learning setting, and there was no understanding of whether interpretability exacerbates or makes these heuristics better. So as a first step, we just wanted to understand, hey, what happens with heuristics when you put interpretability into the machine learning pipeline? But some work that we're doing now is more catered towards, well, how do we get rid of these heuristics? Because the answer is a lot of these heuristics are being applied in this interpretability setting, right? So let me quickly show you some results on sort of to what extent we saw these heuristics come up. And then I'll tell you more about what we're doing now to counter these heuristics. So as a quick overview, we ran a pre-registered controlled experiment with, again, almost 120 data scientists. There were 5 conditions that we had them sort of split up in. We had a control condition where they had to write their own code, do their own thing. There was no interpretability. Then we had the static visual explanations, and this was from 2 tools, one called SHAP and the other called GAMS. And there's 2 of them because we're following one glass box model and then one post hoc explainer for a black box model. And then similarly, we had 2 interactive tools that mirror that sort of explanation technique. And we gave people a Colab notebook to work with. We also had a parallel sort of setup where they were answering multiple choice questions about the data in the model, so we could establish their understanding of the data in the model and any heuristics that were being applied. And we studied them using 2 types of proxies. There were process level proxies, so things like how much time and cognitive effort they were spending, or how many hints were they using to get to the answer. That kind of get at the process of, doing the data analysis and trying to understand the data. But then there were also outcome level proxies, which were more about their accuracy in understanding things about the data in the model. And then the types of answers that they were selecting. The Titanic example that we walked through, there were answers that were accurate. There were answers that were plausible but inaccurate. There were answers that were plausible and also accurate, and then there was completely inaccurate answers. So we try to disentangle which types of options were they selecting in these multiple choice questions. And for those of you interested in stats, we ran some statistical analyses to test these. I'll cover 3 of these results here just because I think they are sort of salient of what's happening here. So if we look at the time spent on task, again, we had expected that the interactive interpretability tools, which are the green last two options here, would keep people more engaged. But instead, what we found was that the amount of time spent on task was 5 times more for control, so about 20 minutes, right, on average. And every other condition, regardless of whether the interpretability tool was interactive or it was visuals only or whatever option it was all significantly less time spent on task. Now, pair this with the results for accuracy. So what we found was that our control condition with no interpretability had much higher accuracy, significantly higher accuracy, about 17% more than any of the interpretability conditions. So again, interactive interpretability, static interpretability, doesn't matter, writing your own code, 17% higher accuracy. And what we found was the control condition without interpretability leaned most towards selecting these accurate options in the multiple choice questions. Instead, when you introduced any of the interpretability tools, people, tended to lean more towards plausible or inaccurate solutions. So if we look back at sort of our hypotheses here, right, our results for visual explanations matched our hypothesis. People spent less time, less cognitive effort, and ended up making poorer decisions in that category, right? But what was really surprising, and Anthony, to your point about interactivity maybe helping, well, it didn't, right? So instead of interactivity falling in this optimally effortful situation, we found it often fell in this survival mode where there was a lot of cognitive effort being spent, less time being spent, and people making quick decisions. We had asked people a lot of qualitative questions as well to get at their experience with using these tools. And what we found was, from this qualitative data analysis, was that there was so much going on in these tools, so many buttons to click, so many features, so many things to understand, that instead of trying to sit down and understand things, people were like, I think I know what's going on. I can just rely on my own understanding of this data to make this, to answer your questions. I don't need to fully, deeply engage with this tool that's trying to give me so much at once. So when you have all of this information coming your way, even when it's interactive, people sort of ended up relying on their own past heuristics to make things easier. Whereas in the satisficing condition, which was just the pure visual, no interaction condition, what they were doing was making quick decisions based on whatever was at the top of the visual, right? Whatever was the first 2-3 things in the visual that caught their attention. It was that visual anchoring. And then with the interactive tool, it was this frustrated use of prior heuristics because there's too much going on. Interestingly, our control condition fell somewhere between optimizing and maximizing. What ended up happening was we had presented people with hints to make the study kind of more doable, right? Because you never want to run a study that's so hard that no one can complete it. So we didn't give them exact code for anything. We didn't give them any help, but we told them, hey, if you wanted to look for certain resources, here are some links that you could look at and then write your own code based on those links. And those breadcrumbs, ended up serving as this more optimally effortful thing than sort of any of the other conditions, where people still remained engaged because they had to write their own code, understand the documentation, work with data. But those breadcrumbs were enough to make it feel less cognitive effort than it would have been otherwise. So the purpose of running the study was just to understand whether interpretability helps, hurts, what does it do with these heuristics in human decision making. And what we found was, interpretability always exacerbates the use of heuristics, no matter what type of interpretability you rely on, whether that's static interpretability or interactive interpretability. So this was like a huge understanding of the underlying human cognition elements going on here. I want to pause there if anyone has any follow-up questions based on it.
The visual versus interactive, one of the things that struck me is whatever you were measuring, the use, the activity, the result, the quality of the result were really almost identical I mean, yeah, was that surprising? Did you expect a bigger difference in those two, or were you kind of anticipating that? And I mean, that it was shocking when I saw the graph. I would have thought that it would have been different, but that's just a heuristic because I was guessing that.
No, I mean, we were also guessing that it would be completely different experiences because we were assuming that interactivity would help, right? It would create this really nice cognitive, optimally cognitive, effortful situation where people would spend a lot of time because they like playing around with things, and in doing so, they would have a better understanding and accuracy about the data. But what we found was, you know, when you overwhelm people in any way, right, they're gonna, and these interactive tools did overwhelm people, they're gonna fall back on their own heuristics. So we have to be more nuanced than just presenting everything in an interactive fashion. And instead, something we're working on now is, how do we present this in a narrative? Because people like that kind of narrative thinking, that kind of, this is building up to something, this is building up to an understanding of something. So these context-free, fully interactive tools don't work because people have to hunt for that narrative on their own, which they don't like doing.
Another point on that, the growing of the answer, the amount of time that you're putting into it. From my background in systems, large, huge systems, we were always warned everybody wants features and everybody wants more feature, interactive, play with the knobs and the buttons, and that's great. But do not overwhelm them, because if you overwhelm them, they will become tired, they will become bored, they will become angry, and they will make mistakes one after the other after the next. Is this leading to a methodology where you gradually increase the usefulness, functionality of the tool suites, that the tools kind of grow with the user as they use? I mean, in some sense, looking at these full features tools, looking at huge networks, looking at large operating systems, is kind of like trying to get a teacup full of water out of a fire hose.
Mm-hmm. No, that is exactly right. I think the unfortunate situation is that these tools are already out there and we didn't develop them. These are being developed largely by industry partners, right? And there's no understanding of what about these tools is actually helping people, if anything, right? So what you described as the sort of slow buildup of understanding, right? Of which part of this is helpful? What do we need to continue to build on? What can we pull away and put in a separate tab that people only access in a circumstance that might be necessary, right? This type of contextual narrative system building is completely lacking in this space. And what we're finding is what currently exists is hurting more than it's helping. I mean, people think, oh, I have an interpretability tool, now I can just offload my decision making on them and sort of trust what they're saying. And that's causing massive overtrust, massive biases to come up. And that's where human AI decision making is really getting negatively affected. Okay, so yeah, I want to get a little bit into, now we know kind of what might not be working, and a lot of it has to do with human cognition and these human-centered properties, right? Again, this comes back to the point of we can present the perfect technical solution to people, but we also have to account for idiosyncratic people things that might be at play. And that's sort of, this experiment made it very clear that human cognition is a huge piece of that. So we had that hypothesis for what's not working and why. We wanted to see, well, what can we do to enhance human AI interaction going forward? And this is where we really had an interesting human-centered connection that I'm curious to hear all of your thoughts on, because I think this is the land where you all operate in far more than we do. So basically, we tried to leverage organizational theory to improve human AI interaction. Now you might ask, why organizations? And our are interested in it was because organizations form when there is a need to collectively process information, right? At their core, they sort of end up being systems of information exchange. So people and organizations not only have to work on their own tasks, but they also share information and establish understanding within a team, and then also across teams within an organization. So if an organization is effective and safe, it must be handling human cognition and sense making and information exchange in a way that works. So let me give you an even more concrete picture of this. So here's what the current high-level conceptualization of interpretability is. You have, training data, machine learning model, explainable model, and this technical solution is intended to help you answer questions like the things on the right over here. Why did you do this? Why not something else? Things like this. When you look at organizational theory, it talks about all of these facets of answering these questions and understanding them that have nothing to do with what is on the screen right now. Instead, these are things about people, things like their identity, the fact that people need to reflect and retrospect before they can truly understand something, people's inclinations to notice certain cues over others, depending on their ongoing tasks, the fact that people believe a plausible and coherent story, even if it's not accurate. And then the fact that, they exist in a larger environmental and societal context, and all of these things affect the information that they understand. So again, these heuristics and biases that we develop, right? Where are they coming from? What part of our cognition are they tied to? These are just 7 properties of sense making that come from large organizations and understanding them and trying to understand how people work within them. One example I want to give of this plausibility over accuracy story, because I find this fascinating in the human AI context, is consider this radiology example, right? So here are some chest radiographs to determine if a patient has COVID-19. And on the y-axis here, you have the classification of whether it's a positive or a negative case. Now, imagine you're a radiologist, right? You're looking at these, you have the prediction from an AI tool, and you not only have the prediction, but you have an explanation. So here's your explanation. It's showing you a saliency map of where in the chest X-ray did the model pay most attention when it was telling you whether it's a positive or a negative case. So I don't know if any of you have medical expertise, but put yourselves in the shoes of this radiologist, right? What are things that you might notice from these saliency maps? Anything that comes to mind? I'll give you a second, and then there are arrows pointing out what you should be noticing actually.
Positives seem to be darker. I mean, in the black and white, they seem to be darker, but I don't know if that's just because of the background or the image that was taken. I mean, they when you take X-rays, they're really careful about how they do that, because if they, I mean, it's like taking a photograph into this. We're going to have that problem next week. Everybody's going to be out taking photographs of the sun. And that may work, and that may wreck your camera, and hopefully it doesn't wreck your eyes, but
yeah, so
there will be some.
I think you're hinting at exactly kind of what I was going to say next, but maybe different terminology there, is that there are lung markers and lateral markers here, right? So in the saliency map, you can see sometimes the arrows are pointing towards dark spots that are in the lungs, and other times they are in the lateral areas of the X-ray that are not in the lungs. So like your diaphragm in the rightmost X-ray, or by your shoulders in the middle X-ray. And a radiologist looking at these, right, has to make that decision or determination of, does this model seem accurate? Is it understanding the right relationships, right? And what sense making an organization tells us is the radiologist isn't quite looking to say, no, this is not accurate. They're trying to come up with a story for why this might be accurate, right? They're often looking for a plausible story. A plausible story that I can come up with for this particular setting very easily is, there's more lateral markers in the positive cases than in the negative COVID case. And this could be because, like the photography example you were giving, Anthony, because when you have, say, COVID, you might be coughing. So there's a lot of focus on, your movement, your shoulders, your diaphragm. And that's why in those x-rays, you're seeing the model look at those features. So it's a perfectly plausible explanation for why the positive cases are the ones where you see these lateral markers. I saw someone, maybe Alex, were you wanting to say something?
Oh, I was coughing. I'm sorry.
Oh.
I'm going to unmute everyone. I don't have a magic unmute button, but I want people to participate. So just a heads up for everyone.
So I guess, at a high level, what we see here is this, again, this plausibility over accuracy determination. That is, again, a very well-known property of human sense making in organizations. So there are organizations that have studied these properties of human cognition, right? Human sense making, these additional factors that have very little to do with what you present to people, and they've still managed to be effective and safe. These organizations are often called high reliability organizations. So things like healthcare organizations or air traffic control systems or naval aircraft carriers and nuclear power plants, where, again, I mean, it's not like they've never had catastrophes, but for the most part, their priority is avoiding these catastrophes, right? And making sure that there's no harm that comes from the main sort of purpose of that organization. So what these HROs is what these are called, high reliability organizations. What these HROs do successfully is similar to the harms and biases that we want to avoid when we're deploying AI systems, right? We want to make sure we're accounting for any of these properties of human sense making that might come up ahead of time. So looking ahead, kind of borrowing from these organizations and their properties, here's an idea that I'm currently very excited about exploring. Inefficient AI for safe human AI interaction. Might sound weird, but let me try to explain this with an example. So imagine a naval aircraft carrier, right? If a naval aircraft carrier was prioritizing efficiency, they would optimize for minimum number of people on the deck that are required to make things work, tightly couple tasks, quickly get things done, super efficient, productive system. Instead, when you look at an actual naval aircraft carrier deck, right, there are at least 3 people for every task. So they have that redundant person, no matter whether they're needed or not. There are supervisors managing each team, and then there's a supervisor just overlooking the deck and making sure everything is working smoothly. And then there are assistants to the supervisors to help them stay on track of things. So for these high reliability organizations, effectiveness and efficiency obviously matters. It always does, but reliability is critical, right? Otherwise they would cause global catastrophes. So they often add redundancies and inefficiencies to make an aircraft carrier or whatever the organization is failure proof. And you all, operating in systems land, know this is QA testing and sort of maintaining that. So borrowing and kind of being inspired by those things, some things that I'm trying to prioritize and design these days are things like seamfulness. User experience research tells us all about making systems seamless and easy to use for everyone, right? Seamlessly integrating them into people's current pipelines. But this is causing a very sort of automated response from people where they just tend to overtrust everything that they're seeing and overly rely on it. So showing some complexities in a system might actually keep people engaged. We could also induce some skepticism, right? Making people question the information they're seeing rather than sort of just letting them agree with the information. So how do we bring about this deep thinking about it? Making people skeptical often makes them think. Also allowing for adversarial interactions with the system. This idea is borrowed from actually red teaming, which again, you all probably already think about a lot in your systems. But not just thinking about red teaming and QA testing at the technical level, how do we create edge cases and test software, but more from a social perspective as well. How do we create group dynamics where different red teaming ideas might come up. So putting a novice and an expert in the same room to try to answer a question, right? So that their differences in expertise causes more question generation, or different roles. So a software engineer versus a front-end designer versus a machine learning designer, sort of putting them together to answer some of these questions together. So what sort of adversarial group composition interactions can we create to make this inefficiency work better for us? So some examples of, things that you've seen today in this presentation that might work differently is, instead of just showing a feature importance visual, and putting this as a code output in someone's pipeline, can we have a conversation about it? Large language models make this possible, right? So we're currently working on a project where we have different conversational dialogues using questions like in the Socratic method and visual narratives, right? How do we convert this one chart into a conversation and make people talk through what they're understanding based on this? So that is to introduce more seamfulness and friction in the system. Instead of just showing the top end features, make people skeptical. Maybe show them the bottom end features that the model did not think was important. It's, again, anchoring them to positive versus negative things, right? So if we say, look, oh my God, fare that people use to get on the Titanic is considered not important at all in making a decision about whether they survived or not. Do you think this is weird? Right? And you can imagine generating these flags completely based on sort of random, placement, or you could do back-end anomaly analysis in the data to generate some of these flags. And again, these are just very simple, easy ideas that we could be doing on top of what already exists. And then again, like I said, this adversarial group composition to engage people in a sort of coming from different mindsets, right? So Slack allows this, or any kind of messaging interface allows this very easily. Imagine you create a bot that brings this into that conversational interface, right? So these not important features and cautionary flags coming up on Slack as a conversation starter, maybe people start talking about it, have more requests for information, and they want to learn more. Providing that information within the Slack interface, having this well integrated, helping people explore more, maybe to the point where they want to go off and do sort of an individual exploration. Again, allowing that in a chat interface, recording their context, anything that comes up in their analysis, bringing it back to the team, having people have a conversation about it and follow-up questions, sort of continuing this process of putting different people with different mindsets in the same team, is something that we're developing right now to see if that improves, the use of interpretable outputs when people are making decisions. But of course, this is sort of, this idea of inefficiency is interesting to me, and I want to see where we can take this. But you can't just prioritize inefficiency. It can't be the only feature of a system. Anytime you're thinking about designing and adding more friction and seamfulness to a system, it has to be done just right. Otherwise, we end up in the case of being too cognitively burdensome. So we have to maintain some notion of usability. Again, you can introduce skepticism to make people think deeply, but we don't want them to be too skeptical. There has to be some level of trustworthiness to balance it out. Otherwise, they'll just stop using a system. And then similarly, for adversarial interaction, you might encourage people to think in different ways and sort of, counter each other. But at the same time, to do a task well, you still need some shared understanding and team cognition within a team as well. So balancing these positive and negative elements is where I think there's going to be a lot of tricky challenges, and I'm excited to sort of, start with some inefficiencies, but see where that goes. But yeah, so that's sort of where my research is headed these days, and I hope this conversation has helped you think a little bit about understandability, trust, over-trust, interpretability, where things are at, and where things might go if we had more support from organizational mechanisms that are sort of well-known, that are well-tested. My cat is trying to interrupt, so let me move on to my last slide here. I hope this has helped you, see where an understanding of how people think, communicate, and collaborate can help with designing effective and safe human-AI interaction. I'm happy to take any other questions that you all have.
Thank you very much.
Does anyone have questions? Feel free to unmute yourself.
I was at the gathering that Mats Heimdall had the other night, AI and health.
Yes.
I don't remember the exact title. It was AI and healthcare. And I listened to the different presentations, and there were some presentation. They were all presented as this is work that we're doing in the AI arena. So we have that as a boundary. This is AI stuff.
Mhm.
And I looked at it, and one of the things was attach a sensor and collect electrical impulse data, and we have to do that for a long period of time, maybe a day, maybe a week, maybe a year. And then we have a huge amount of data, and how do we take and find the anomaly in that? And it was, let's use artificial intelligence to find the whatever the anomaly happens to be. I mean, I'm not a medical doctor, and I'm not that well versed on AI, but really that didn't sound like an AI problem to me. That just sounded like a crunch the data. This is an algorithm that we've had for a long time. Doctors have known what the anomalies are, but to look through 10 exabytes of data, they don't have time or interest to do that. The person will be dead before that's ever happened. Is some of AI getting mislabeled or misappropriated just because we have a lot better computing power?
Yes, I 100% agree with your perspective there. A lot of, especially in machine learning, because we're talking about crunching a lot of data to understand that data, right? Which people would have to look through each individual input data point to start forming those patterns. I like to think of a lot of these machine learning models as essentially pattern recognizers, right? So we're not talking about, a lot of times now these days when we're talking about AI, we're talking about pattern matching done at in an efficient way because of the computational resources that are available to us now.
Thank you.
I think the challenge, if I may add to your question a little bit, is also that someone has to verify those patterns. When it was just people looking at this data and trying to infer patterns, people were also describing their reasoning behind finding a pattern. With AI, it's oftentimes not able to communicate its reasoning behind finding a pattern. And as you might have inferred from the talk I just gave, oftentimes people overly still rely on it without diving deep into the reasoning and whether that's accurate. So that's where things get really tricky, is when we start using these systems to help us out without knowing why they're making the predictions that they are and the patterns that they're understanding.
Put another way, from the way that I used to always debug stuff back in the old days, when dirt was new, was you'd look at something and you knew what the answer was supposed to be, and you didn't get it. So then you've taken and worked backwards through your code, through your data, to figure out, was it a data anomaly? Was it a coding error? Was it multiple interrupts happening on this? And that can be hard and tedious, but that's what I call the classic way of debugging and building software. In some sense, with AI, you've got these global conglomerations of information. It may not be possible to reverse engineer those back to the supporting subsets or the supporting individual data points. And if the problem is with an individual data point, that's going to be hard. That's going to be even more difficult to debug that.
Yeah,
Why wouldn't that be possible?
I think in some ways we sort of assume that there's a semantic understanding of concepts happening here, where oftentimes that's not, right? So a machine learning algorithm might be able to tell me that whatever is in column A affects column C in this way, but it doesn't understand that column A is age values and column C is income values, right? So it is making those pattern matches happen without that semantic understanding. Now, in some instances that works because there's a human in the loop that's sort of doing that semantic understanding process. But it doesn't always work when the humans themselves don't have known sort of heuristics about those columns, right? So you might be looking at a new tool that was launched by a company and we're just getting huge amounts of user logs back from it, and we don't quite know what the relationships between those user features are yet. So without a human trying to do some initial recognition of what's going on, it just becomes a completely black box process because the AI doesn't rely on that semantic understanding.
So the AI isn't relying on semantic understanding, but what about the actual end users, not the data scientists? How are they going to actually understand and interpret this data if the data scientists are even having difficulties figuring out if there's issues with it?
Yeah, that's a fantastic question, and I don't know the answer yet, right? Because this is part of what we're trying to explore now is all of the results that I presented to you are with data scientists. And as you can see, they don't understand a whole lot of what's going on. So I don't think we're at a place where we should be launching these AI tools with end users, just in the wild, just because if the data scientists don't understand it, how can we expect end users to understand it and use it? For example, AI is being used in some medical settings now, right? The doctors don't fully understand the outputs of the AI tools. The machine learning people who built the AI, the models don't fully understand it. And the doctors are supposed to provide a reasoning to the patient for why they're accepting or not accepting the AI tool, right? When there's no connection in any of these and understandability in any of these elements, that's where you see bad cases happen, like biased, prediction towards Black people, because there's not a lot of historical data on the healthcare aspects of Black communities. Similarly, you see biases in AI sometimes giving wrong dosage predictions for how much dosage of medication is required for a patient. We're seeing these errors come up constantly, partially because there isn't an understanding, and we're trying to approach this as a design problem, right? How can we build on that understanding and make sure people are seeing kind of the outputs and not just visually seeing them, but understanding them? But we don't currently have an answer to what would it mean for an end user to understand these outputs. And yet these
When
tools.
somebody detects that there was actually some bad output, is it possible to go back to the bad data and actually fix it at its source? Which I know in a lot of cases is in China, right? So
yeah, that's sort of continuous monitoring and feedback, right? That's especially done in software, and has historically been done really well in software. That pipeline hasn't been created in most AI systems yet. A good system should do that, but whether the organizations that maintain these models and systems do it is a completely different question. And what we found is they don't often do it. Unless there's a big splashy news article that forces them to do it.
Usually a negative, splashy news article. So I asked the question earlier, why couldn't you go back from the point of seeing an error, an apparent error in the data saying, this doesn't make sense? Why couldn't you go back, or better yet, ask the AI system to go back and tell me where that diverged from your expectation?
I think theoretically you can, right? These systems do allow for capabilities, especially if we convert this into a more natural language format, for it to become even easier for people to ask that question. It's more, I think, also, I mean, there's the technical route, right? That you could technically do this, but what we're seeing often is this human problem of convincing people to do it or making them think that they should do it, right? So whenever people see a prediction, oftentimes they're like, okay, it's done the computational work for me, and look, it's even providing an explanation for why it's doing it. what that explanation is intended to do is to serve as a deliberation tool, right? Look, here's an explanation. Think through, does this make sense? If there's an error, go back. But the processing stops there, where they see the explanation and they go, okay, it's given me an answer, it's explained its answer, everything must be good, I can move on, right? So it's that we need to encourage people to engage in that loop that you're talking about as a human problem, rather than say the technical feasibility of it, which does to some extent exist.
Does, do you know of tools that not just provide the capability, but actively support it, and present it as something that is easy to do and should be done, as opposed to, oh, there's this feature buried down somewhere in the menu, and a footnote in the documentation.
So we're still in very early stages of interpretability and explainability. These concepts were introduced for the first time in 2016 or 2017, and then put into tools by 2019, 2020, right? So most of these tools exist as coding sort of modules that you can use and bring into your own pipeline. So for example, if I'm working for Microsoft, right, and I have my Python code that I'm writing to do some data science work, then I can bring in an existing tool that provides explanations on top of the code that I'm writing. It's a module that you can add to your code, but there aren't systems where this is just embedded as a part of, you know, everything from the get-go. They're still sort of relatively new in people's pipelines.
What you're describing is making a functions library.
Yeah.
You know, like system used to do, and your function library is thin and weak right now.
Yep. So there's both that the functions library is weak, right, and needs improvements upon sort of how it's integrated, but there's also the motivation to integrate it is largely missing. And when it is integrated, you know, it's used in a very superficial way, right? There isn't full integration of the kind where you would be continuously monitoring and providing feedback, where you would be doing anomaly detection and sort of pinging people to error check and test things. It's still very superficial.
So we've invented the 21st century analog to a computer, but haven't yet learned how to use it.
In some ways, yeah. And we're realizing that there's, you know, challenges on both sides, technical and social sides and organizational sides, because a lot of this work is being done in large organizations that is hidden from the research community. So it's hard for us to audit these systems. It's hard for us to test them in ways where we have access to. So take, for example, ChatGPT, right? It's maintained by OpenAI. It's a black box. We don't know what sort of deep learning or any other machine learning techniques they're using to build ChatGPT. They can explain it in a hand-wavy sort of high-level way, but we can't investigate it in any way. So that makes it incredibly hard to audit and say, this is what the model will do wrong. This is where it's going to go off the rails. All we can do is test these one-off edge cases every time and see if there's any response, unexpected response. But that's not a very principled approach to doing this.
And the other thing that seems like it would be very useful is to use the tool to automate the process that is necessary to validate the tool, which sounds very much like the whole training procedure.
I think it would be fun to try to automate some of this process, and certainly we're interested in doing that. But when you think about any kind of decision-making setting, right now, the agency is still ultimately with the humans, right? So it's also not just automating the process, but automating the parts that don't need human oversight and keeping the parts that do need a human oversight. And what information does the human need from that automated process to continue to still be aware, right? These are all open questions, but yeah.
And it's a set of questions that I think is most appropriate to be asking of seasoned data scientists.
Or I
How-
really, I mean, I think software companies or people who've maintained legacy software that you all have, you've seen this full cycle happen. It's just happening again with AI now. So Mats, who is sort of your connection at UMN, and I talk a lot about how QA testing first got started. What was the motivation? How did that process come about? What was the red teaming element behind it? Just so I can try to import some of it into this AI wave that we've got going on right now.
I think that's definitely a good approach. I was the reason I mentioned that asking the questions of the data scientists is that one, to avoid the overload of data that you had talked about earlier. It would be helpful to figure out what is it a data scientist does when they're sitting in front of the computer, looking at that chart, changing those dials and sliders and views of the visualizations of the data set.
Yeah,
And
and the
what
challenge.
of that can the computer take care of and then use the AI to explain the results of what it did, or in addition, perhaps even more importantly, explain what it didn't do.
I think that's exactly, I mean, the approach we're trying to take as well. And something that comes up as a unique challenge there is, when people become experts at anything, a lot of what they do becomes tacit knowledge. So they're not even fully aware they're doing something as a conscious step. It just becomes so much a part of their pipeline that they just kind of do it all the time without thinking about it. And capturing this tacit knowledge is very, very hard. So one approach that we're trying to take to capture some of this tacit knowledge is, what if we put a novice in the same room as this expert data scientist, and then have them do a task together where the novice is asking questions and trying to learn from this expert data scientist as a part of doing this task together, instead of us probing the data scientist in an open-ended way. Doing this task together becomes a more of an anchor, just to get at that tacit knowledge that we might miss, that data scientists aren't even aware they're doing. So we're definitely very interested in taking that approach to finding out what's going on in the process here.
So if you replace that novice with an untrained AI system.
Yes, that is also one of the conditions. Yes.
But one of the benefits in doing something like that is obviously training a system at the same time, but forcing the data scientists to verbalize what they're doing. If you, for example, took the keyboard away, so they had to perform voice commands to make any modifications or changes of visualizations, then just that act of saying out loud what they're doing will bring out all of that tacit knowledge.
Absolutely. And I think even if we can't completely take the keyboard away, right, something where I see large language models as really an opportunity is their dialogue and conversational ability, right? So taking away the expert's ability to write code and do something with the data, but still having the ability to converse with a dialogue agent, to talk about sort of what they want to do with the data, and then seeing what kinds of things do they come up with, what kinds of questions do they want this dialogue agent to then go run in the background. Again, instead of the voice capture of something, it could be a text-based capture of their tacit knowledge. So that's also what we're trying to explore.
Any other questions?
Just kind of a question. When you show the example of that outlier data that was bad data, are there systems in play where with data scientists where they override the bad data, like pull the median out of the data set, and so it magically just disappears rather than trying to correct the base data?
Yeah, so definitely there's a lot of work on anomaly detection that automates some of this process, and people are able to quickly find these outliers and remove them, right? But the example that I showed, what was happening there was, imagine you have a data set where one of the columns, say 10% of the values are missing, right? So the data collected has some missing elements. Oftentimes, what data scientists do in this setting is they take the mean value of that column and put that in those 10% missing columns to complete the data set. And the simple act of imputing these values with the mean, as you can see, can create sort of weird functions that the model then overfits on, right? So anomaly detection and sort of picking up, removing those outliers does happen, but sometimes even in fixing a data set, you can create these unique outlier overfitting situations that happen.
Hmm. Yeah.
Several of us have had work in actual visualization of medical images, and they would use algorithms to try to colorize, usually maybe a Markov process or something. And exactly that, they were basically overfitting the data that didn't exist to try to actually give to the radiologist what was there and digging information out of the data.
Yeah, and this kind of data leakage or spurious correlation, what they call it, is very common with these types of pattern matching things that are going on. And so, for data scientists, I think this is something that they think about all the time, and that's why we were surprised that even when they had access to tools that are supposed to sort of make you think twice about some of these data leakage problems happening in visualizing the data as they do, instead of that being a cause for concern, it was often just, I remember this quote so well, but one of the data scientists told us, this is a publicly available tool. Microsoft sponsors this tool. If anything was wrong, it would just tell me. So there's just this complete mismatch of mental models of capabilities, right? Instead of it being a deliberation tool, it becomes an automation situation when it shouldn't be.
It's automating the wrong thing.
Exactly.
Any other questions? Well, I'd like to thank our speaker this evening for a very interesting talk. I think a very relevant and timely talk with the way technology is flowing these days. Look for an email for next month's planning meeting. And with that, I think we'll end this evening. Thank you.
Thank you for having me. It was great talking to you all for a little bit.
Thank you much. Good night.
Yeah, thank you very much.
Thank you.
One quick comment.